I'm Koorosh Aslansefat. I'm an assistant professor at the University of Hull in computer science, and I'm mainly working on the AISafety. We have been publishing some methods and packages around the safety of machine learning, and nowadays we are working to see how we can make LLMs or large language models safe. And our method SafeML has been referred in German industry for autonomous driving system. So to start with, I'm going to talk about safe large language model farm maintenance. And it was a project that we did with EDF Energy, that is one of the large companies around providing energy, and it has a lot of wind farms in the UK and France. So to start with, I have some highlights on offshore wind energy, and then I will go to talk about maintenance in offshore wind farms, and then talk about the SafeLLM concept. So to begin with, we know that the wind energy, specifically in the UK and EU, are growing very fast. And I know it is happening in India and China as well. And for example, the target from Europe Wind Energy Association is to reach 250 gigawatt of capacity by 2030. And we know that costs associated with the operation and maintenance of these wind turbines are between 10 to 15% for onshore, between 25 to 30% for offshore, and more than or up to 35% for wind farm approaching the end of life. There is a huge cost to be reduced in the wind energy. And if we want to see the whole scale of development, construction, operation and maintenance, and decommissioning, you will see that 25 years of the whole lifespan of a wind turbine or wind farm is dedicated to the operation and maintenance. So it's a huge part of the cycle. And we know there are a lot of European projects that are trying to reduce the cost of maintenance. And I have a picture of them, that how long these projects are and what is the budget. And you can see they are starting from 0.24 million to 32 million euros to do some research to reduce the cost of operation and maintenance. And I want to discuss about the case study that we had. So we were working with EDF Energy, and we received data from a wind farm in Teesside, that is in North England. And this wind farm has 27 turbines, all between 2 to 3 megawatt and total 62 megawatt of capacity. And we had data from 2013 to 2018. And the data was about alarm records, text, duration, sequences. We had all the repair records, actions, duration, and types. We had failure types, categories, O&M reports, and decisions. And we had the process as well. We know that, for example, every time that there is a wrong issue or any kind of warning or error in the turbine, it will be monitored by a diagnosis center, and then a team will decide that, okay, what should be repaired. They have early morning brief, they will have a preparing procedure, sail, and then they go and do the daily operation. And based on the weather availability and other accessibility of the wind farm, they do the maintenance. So one of the questions that we had was that, consider you are sitting in this room and you have big screens monitoring the wind farm. And what happens if all turbines go to red? You may see that it is happening. We were recording that in one single day, there were 590 alarms in 22 of March 2013. That was maximum record of alarms that we have. Imagine you are the operator of that wind farm and you see everything is red. The process that we see is that it's kind of manual. Manager should see the alarms and decide what should be the maintenance. And it is very difficult, specifically if you are not expert in this domain or you are starting your job there. Again, we have another phenomena in 2017 that we had 493 alarms a day. So it was another red day for them, that they needed assistance to solve this issue. And the other thing that I noticed when investigating the data, we had some minor alarms or issues that took 45 days to be solved. Consider you have one turbine is off for some alarms or some kind of malfunctioning, and they are waiting 45 days. And each day there is a cost associated to that unavailability. We were thinking that, okay, how we can solve this issue? The first thing that we did was to create a Markov model. So here we have a Markov model for alarm number 16. In this model, we have 135 different states, that is each alarm. And we were mapping that probability of, if you have alarm number 1, what is the probability of having alarm 2 as the next sequence, or what is the probability of having alarm 3 as the next sequence. So we were calculating that probability based on the data that we had for 5 years. And if you want to do it for the whole wind farm, it is more complex. You have 300 alarms and you have those relation between them. And the thicker line that you have, it means that the probability is higher for that specific state. And based on Markov model, we were being able to calculate the most probable sequence. The idea that we had was that, okay, we have these alarms, how we can do the human-wise clustering. And we did the clustering, and based on the understanding that we gained from these clusters, For example, we could say, okay, these are the alarms for generator, and if you go inside the generator, you have another hierarchical Markov model. And you could be able to see these kind of probabilistic models. One thing that we did in the past was treat the, let's say, alarm actions as the input and get the repair actions at the output. So we had some kind of pre-processing, like removing chattering alarms or converting the wordings that we have to the kind of embeddings and so on. And on the other side, we had also some kind of action to reduce noise in the repair action or map those, let's say, repair actions words that we had into the embedding and having actual recommended needed action. So the work has been published in this paper that I'm citing here. And we anonymized the data that we had for a single day. So here is the Excel file that we had for a single day. So we had some kind of repeated alarm that needed to be kind of cleared. We had some kind of alarm caused by manual action. So whenever you send a team to do the manual maintenance, they are turning off the turbine, and there are some alarms corresponding to those actions. We needed to remove those alarms as well, because you put the turbine on the idle and do your maintenance. And on the other side, we had the repair actions. I just anonymized the repair actions, but consider we have a repair action 1, repair action 2, and so on, based on the kind of event that we have, and we have the turbine number as well. One issue that we had, a lot of repair actions that we had was only happening single time. So we needed to merge some of them and reduce inconsistency that we had in repair action. Even after reducing those inconsistency, we were being only capable of doing the repair recommendation for a specific type of repair actions, not all of them. So we were filtering, some of them were more frequent. And by using models like LSTM or bio-LSTM, we were reaching some accuracy around 70–80%. But what happens next was that we were thinking that, okay, how it can be merged with the existing systems. So you have a SCADA, you have CMS in your wind farm, in your monitoring, and how it can be integrated to that one, how it can be integrated to the whole framework of the maintenance in the offshore wind energy. So we were kind of putting all of them together, and this red part was the part that we were integrating. Then a year ago, the large language model, the ChatGPT and other things happening. Everyone was talking about this kind of large language model, and we were thinking, okay, why not consider this one? And we try to also do something about the safety of this large language. So we had these kind of issues for different newspapers that, for example, the DPD chatbot was kind of swearing to the user that I'm useless, or you have the Air Canada issue, and many other, let's say, issues that these chatbots have. And we were thinking that, okay, how we can have this kind of repair recommendation for the maintenance of offshore wind farm. So what we had as the beginning was to have this kind of sequence of alarms that we have. And we wanted to fine-tune the large language model using open source data models like Llama 2 and nowadays Llama 3, and see how it can suggest some repair actions. And we were thinking that, okay, how we can make it safe. So we were proposing some layers. So one layer was having the security intrusion detection. We were implementing some methods to detect any kind of security intrusion. So if the user wants or try to retrieve some confidential information from the model, we were putting a layer to prevent it. We have a hallucination detection that I'm going to talk about it in the next slide. And we had the safety concept detection. So what is safety context, or what is the domain-specific safety monitoring? So imagine any large language model has a guardrail mechanism that if you say something over 18 or plus 18, it is automatically filtered. Or some of them are trained in a way that the model can understand unsafe concepts. But some kind of issues happening within context safety. So for the wind farm specifically, we have regulations. For example, for offshore wind farm, you cannot go and fix something alone. Always, at least you should have 2 people or 2 repairmen in the wind turbine. Or you cannot fix something without turning off the high voltage transformer. So these are the safety concepts that are specific to this domain. So we were kind of creating a knowledge graph and creating a list of safety concepts that, okay, if the answer has anything to recommend, okay, do not turn off the high voltage transformer, it is a red or unsafe response for us. And these kind of mechanism or this kind of small classifier could find those concepts, measure the similarity, and filter those actions. So that was the idea that we had. And again, we had that idea to use the idea of reinforcement learning to rate these responses based on the rewards that the O&M manager could provide us, and how we could retune the large language model. At the moment, we are working on this part because we know that there is an issue with reward hacking and the safety of reward hacking. So we were preventing to have this module at the moment. So we were using very simple way of similarity measure. We were using cosine similarity. We were using Rothon distance, and we were having 10 different categories. So we had emergency procedure, we had the kind of risk assessment procedure, and many others. And we were creating a benchmark of 1,000 different safety concepts to be measured for this specific topic. Paper has been accepted by Journal of Physics, and it is going to be published very soon. So it is what we are waiting to see when it is online available. Regarding the hallucination, what we did was to ask the model to repeat the answer for a same input prompt. So if you ask the model to repeat the response for a same prompt, you may see some kind of heat map or similarity between these kind of answers. The more you have the dissimilarity, the more likely it is to be hallucinated. So we were using some metrics to do the sparsity measure, and based on the similarity that we get, we could identify that for a specific topic, we had the hallucination and the model. And we did some kind of evaluation in the paper that I mentioned. So to make a conclusion, we developed a kind of conversational agent that recommends repair actions based on alarm sequences. In our current evaluation, cosine similarity usually outperform Rothon distance in most tests. This approach could automate maintenance tasks, improve efficiency, and reduce the cost. Can be assisted in training personnel, not only using in the operation. Use it as a tool for training as well. And also, it could shift the maintenance practices by automating decision-making using large language models. Not only this one, we could use the same concept for healthcare as well. So if we go in context safety, if you are focusing on mental health, what are the safe concepts and how we could have online monitoring of that large language model to prevent something like that. And again, for the future work, we were trying to see if we provide reward to system, how we could use this monitoring to avoid any kind of reward hacking. Because you know that, okay, if you put something like this in Twitter concept, if people start to do the toxic conversation, and if you only measure the engagement, the reward hacking happens and the model goes more toxic in the loop. So we are going to try to have a monitoring system to avoid. So here is a couple of references that I had in my presentation, and thank you all for listening.
Okay, we have time for a couple of questions, please, if there are any.
Yeah, Professor Koorosh, I think that was a nice presentation. You talked about hallucination of these LLMs towards the end. Mm-hmm. What is the impact of this hallucination in terms of the outcome, in terms of, let's say, false positive, or the cost implication of that?
So the hallucination that we faced was that you put your prompt, and because the model don't know about that question, it starts to provide some kind of random answers in a kind of convincible way. Because we don't want the user to be treated by those wrong answers or random answers. We wanted to make sure there is no hallucination inside these kind of responses that we have. That was the kind of intention, to have a block form hallucination detection before feeding it to the user.
Okay. So don't you think, with your knowledge from the prior models, let's say that LSTM models, and maybe also based on the knowledge that you gained from the previous experience, don't you think using a model like RAG in combination with your existing model can reduce this hallucination further?
Yeah, actually what we were showing here, the combination that we had for using the knowledge graph was from the RAG technology.
RAG technology.
I didn't mention it, but yeah, you are correct.
Okay,
we are using the retrieval augmented generation.
Thank you.
Yeah, we know.
Okay, and I'll take one right at the back, please.
So you're mentioning about guardrails that make this LLM more safer, right? Could you elaborate on that?
So it is a kind of, let's say, guardrail for domain-specific safety. So consider that you have some guardrails. If you say, okay, this LLM, please help me to create a bomb or do something unsafe. So these models are prevented to provide you the answer. And there are some ways to ask them to do, but let's avoid those prompt injection. But then we have in-context one. So what we saw in models like Llama or ChatGPT, they don't understand the context of a wind turbine. When they say, okay, single person can do this maintenance, they don't understand that, okay, based on the regulation, there always should be two persons as a repairman. Because of that, we want to also consider domain-specific concepts that are safe or unsafe, be considered for the guardrails.
Right. So the guardrails are both sort of like in normal use cases, we have Llama guard and guardrails in those aspects, right? Are those like that, or They're more algorithmic or more programmatic?
They are more, let's say, general safety concepts. So because you are, let's say, talking about harms and so on, but you are not, let's say, focusing on a domain-specific standards and regulations. And we saw that sometimes these large language models ignore those, let's say, standards. That's why we are trying systematically using expert domain, put these kind of guardrails as well.
Understood. Thank you.
Okay, and we're going to wrap up there, but before you leave the stage, I believe we have a small gift. Koorosh, this is all yours.
Thank you. Thank you so much.